Welcome back, folks. I'm Paul Cuban. Students that are up here now have worked very hard and long to get their degrees. Most or both of them, I think, worked full-time jobs all through getting their degrees, and they had the determination to keep going, and better late than never, right? So congratulations, it's finally happening, guys. Nick Montgomery and Chuck Tucker.
Thank you. We'll get started. Good morning, everyone. My name is Chuck Tucker. Nick Montgomery here. We're going to talk to you about a remote monitoring system for a substation DC battery supply.
For the overview, we're going to go into the introduction of Big Rivers, the problem and purpose of the project, the design, different components of the project, the wiring details and programming, the system evaluations and the different tests involved, economic considerations and costs, and conclusions and acknowledgments.
Introduction on Big Rivers. It's a member-owned generation and transmission utility located in Henderson, Kentucky. Founded in 1961, have approximately 1,800 megawatts of coal-fired generation. We use about 1,300 miles of 69, 161, and 345 kV transmission lines. We have 23 substations scattered across 22 counties. This is a system map for Big River Systems, stretching in the east in the Jackson Purchase area, near Paducah, all the way up to the west and the far east to near Louisville in the Meade County area, and the center section is the Kennergy area, service area. And our 23 substations are scattered throughout this region. Henderson County here, and the project site is at the Reed substation.
The purpose of this project was to provide a design for a 125-volt DC battery bank located at the Reed substation in Seabury, Kentucky, that transmits and communicates information back to the Big River's main headquarters located in Henderson, Kentucky. The North American Electrical Reliability Corporation, PRC 005, was incorporated for reduced maintenance intervals of routine monitoring checks of battery voltage and ground monitoring.
The site for the project here at the Reed substation, located in Seabury, Kentucky, is at the Seabury Station, Seabury Facility Power Plant. The building in the background here, the left side, is the location where we installed the battery monitor for the project. Substations are typically used for stepping voltage up for transmission voltages, or stepping voltage back down at the distribution level for homes and businesses. This particular location is where we're bringing generation basically to the Big Rivers, to the grid.
The problem statement located here is the C&D battery charger and the 125-volt DC battery bank that's being monitored. The problem is that the C&D battery charger only requires power going back, and there's no means of communication going back to headquarters, which means that personnel has to physically come out to monitor the batteries instead of being able to monitor them right from the headquarters. A 125-volt DC battery provides power to protective relays and various other monitoring equipment located in the substation. Failure of the DC battery causes loss of control and status of equipment, including power to circuit breakers. There were two options for this project. One was to upgrade the C&D battery charger, and the other one was to install a new device to monitor the batteries.
This one-line overview shows a typical representation of a control scheme topology between our headquarters dispatch, energy control, and a typical substation. The area in red shows the new battery monitor, where it fits in the picture. And what we have here, the Big Rivers utilizes a microwave ring that we communicate over. It is a private network that we developed back in the early 80s. It has since migrated to a fully digital microwave system now. We transmit to two dispatch centers. We've got an emergency dispatch center and our main one at headquarters location in Henderson.
For the basic design, this is basically everything located in the substation, in the Reed substation control room. And depicted in red is the new battery monitor, and the ARGA it's just basically a brand name. There's 6 conductor number 18 communication cables that go back to a remote terminal unit for the communications back to headquarters. There's also a 2-pole 15 amp circuit breaker that was installed in the DC power panel went back to the monitor for main power. The CND charger is still going to charge the batteries, and all that gets charged back to the main DC panel. The main DC panel is powered by various substation controls, including relays, meters, fault recorders, sequence of events, and emergency lights.
This shows the front panel display of the ARGA battery monitor that we selected for this project. It's manufactured by ARGA Controls, a division of Electro Switch. Across the front, you'll notice there's LEDs to display positive to ground, negative to ground, high voltage alarm, low voltage alarm, and there's also in the bottom left-hand corner a pulsar switch that's selectable for an option that we utilize. And the option is a actual ground fault detector handheld unit that a technician can use in the field. If there happens to be a ground alarm comes in, they'll use this device to troubleshoot each DC circuit. This particular location had 3 DC panels, so roughly 30 circuits that we could have a ground on, and we would be able to utilize this to trace each circuit one by one and find and isolate and eliminate the ground.
Depicted in the red area is the area for installation to the monitor. As you can see, it's going to be located right next to the battery charger and the DC battery banks. Right next to that is the main DC power panel where the battery monitor is going to be powered from. It's going to be mounted up, or it's going to be mounted against a NEMA 12 Hoffman enclosure, and there'll be 2 flex pieces of conduit, one for power, one for signal that goes back to the cable trench, and then there'll be communication cables going underneath the cable trench through a cable tray back up to the remote terminal unit. The reasons for location was it was in close proximity to the remote terminal unit, the DC power panel, and the 125 volt DC batteries, and it was also easily accessible to employees.
The Hoffman enclosure was a NEMA 12 design that we utilized or indoor application. There was no need for it to be outdoor rated. The size was selected due to the depth of the battery monitor, the rear terminations on it. We selected enough depth in the panel in order to eliminate any shorting or grounding of the connections once made, and it's on a hingeable, removable cover. The 4-inch cutout was made by on-site at our Seabury machine shop, which actually used the CNC water jet. This is a picture showing the enclosure as it received before we did any modifications to it.
So what shown here is the inside view of the main DC power panel. As you can see on the before installation picture, there was plenty of spare points to be used, which means that there was plenty of capacity, which is the reason why we chose this panel for our main power. As you can see in the after installation picture is the 2-pole 15 amp circuit breaker shown in slot 16.
The remote terminal unit, or RTU as we call it, is the repository where all the control digital analog signals to and from our dispatch center are processed. This particular unit was just an older RTU was replaced in December of 2015, like this last year, and that's where the output wiring for the ARGA battery monitor resides now. So we've got the 0 to 1 milliamp output, as well as our alarm set points are wired directly to this. We also had to assign the point assignments to reside in the RTU. I worked with a SCADA engineer on that at Big River's headquarters.
The terminal blocks were used to allow for junctions going to the device, and the wires going, the communication cables going back to the remote terminal unit. It allowed for testing and isolation without disturbing any wiring. The main power was connected straight back to the device because it was in close proximity and there was no communication necessary. Here's a picture of the installed terminal strip. It's installed in the back of the Hoffman panel backplate. On one side is single conductor number 12, wires going back to the device. On the other side is the communication cables going back to the remote terminal unit. The wiring detail here shows the DC panel number 3 with a 2-pole 15-amp circuit breaker. There's 2 single conductor number 12s going back to the battery monitor. Depicted on the box here is the terminal strip. And on one side is the single conductor number 12 going back to the battery monitor. On the other side is the 6-2 conductor number 18 communication cables that go back to the RTAC remote terminal unit. One of them was used for the 0 to 1 milliamp analog output voltage indication. One was used for reset. One was used for positive ground. One was used for negative ground. One was used for high voltage and one for low voltage.
This cable routing shows a slide, shows a point-to-point cabling and the conduit routing that was utilized. Inside the control building, there was an existing in the floor cable trenchway. It's typical of our substations with removable diamond tread plate covers. So you utilize that across the bottom section here for running the length of the building. So there was no overhead cable trays in this application. It's all in the floor. The programming screen here shows some screenshots of what was done in our SCADA, or supervisory control and data acquisition system. What we have here are screenshots that show the actual points and the representation. This one here is identified as the 125 volt DC battery voltage. It's a 0 to 1 milliamp output that comes into our OSI Monarch system, software SCADA system. This is actually scaled to be from 90 to 180 volts DC, 0 to 1 milliamp. The bottom screenshot shows the actual positive and negative ground alarm set points that are represented with a contact closure right off of the unit itself. And these pick up at a predetermined set point, 13 volts, negative or positive. This is an actual screenshot that the operators in our dispatch energy control see. The red arrows depict what were the additions for the ground alarm that show whether they're in normal or alarm. That would also generate an alarm on their alarm page. In the far right, you see the actual voltage, which is actually displaying, and system checkout performed perfectly, and representation of the actual field conditions of the display unit and the OSI screen at dispatch were perfect.
For system evaluations, there was 2 things that really needed to be evaluated: the power to the system and the communications going back. The power to the system was tested once the circuit breaker was installed. We basically just turn the switch, the circuit breaker on, turn the switch to the monitor on. As you can see in the picture here, the voltages read the exact same, which means that the power was monitored and tested correctly. The communication was then tested once the communication cables were installed back to the remote terminal unit. All the address points were taken back to headquarters and programmed, and it displayed perfectly on SCADA screens back at the headquarters.
For economic considerations, we had a couple of options, as we mentioned, that we were under consideration. The first option was strictly a hardware upgrade to the existing C&D battery charger. This required an additional circuit board at some expense, and it also had some limitations, one of which was a 50-foot range on RS-232 connection. And since we were dealing with a much larger application in the building of about 75 to 80 feet away, we were afraid to use that consideration. Another issue or negative was the loss of AC power to the charger was critical to getting the communications to the battery monitor, and we felt like that would not be a reliable means in the case of a upset or an event, a switching event in the substation. We may lose the control or the vision of what the battery voltage was doing.
Option 2 was the option chosen. It was the most cost-effective option, and it was also easy to install, and there was no cable restrictions, which means that you could use standard wiring for your communication. And it also only required DC power, which means there was no fear of losing the AC, which means that if the loss of AC would have meant everything would have been lost. For the bill of material, we had the battery voltage monitor, the NEMA 12 enclosure, the 12-state terminal strip, the 2-pole 50-amp circuit breaker, and the communication cables, and the total cost of material for this project turned out to be $2,400.
On the labor cost, we kept track of Nick and myself's time, as well as all the other labor crafts involved, as well as our SCADA engineer that helped out with the project. And we basically ended up with an engineering / design total of 185 man hours spent for the project. Programming and installation ran in around 46 hours for a total of 231 project hours. We used some budgetary numbers because Big Rivers does not publish any kind of labor rates. So based on budget numbers, we were able to come up with a grand total labor man hours of $27,526.
In conclusion, it was initially thought that the C&D battery charger was a logical choice, but after further evaluation, the C&D battery charger upgrade was a logical choice. But after further evaluation, the voltage ground monitor was proved to be the right choice and the cost-effective solution to the problem, and it met all project requirements. It also, once installed, it displayed perfectly on SCADA screens throughout the Big Rivers Energy Control.
All of our project timelines and deadlines were all met satisfactorily, even a little ahead of time, and it was very successful. Big Rivers Management is currently considering to implement the same installation on other substations where we do not currently have any solid-state relaying that is capable of reporting the same type of information on our battery system.
For acknowledgments, I'd like to send special thanks out to Big Rivers for allowing me to work with Chuck Tuck on this project and gain some experience on the project. We'd like to thank Dr. Cuban for meeting with us each week to discuss deadlines and for sitting in on our preliminary and dry runs. We'd also like to thank Mr. Eller for sitting in on the preliminary review. We'd like to thank Dr. Mitchell, Dr. Goodman, and Mr. Nelson for attending our dry run presentation, and a special thanks to Donna Moore for the necessary reminders to keeping us on schedule. I'd also like to thank Apex Engineering for showing up and working with me throughout the years to attain my engineering degree.
Are there any questions from the group?
All right, questions? There have to be some questions.
Based on the success of your project, do you anticipate deployment of more of these units throughout the river system?
We do. It's presently under consideration now, and like I mentioned, Big River, since it's been around since 1961, we've got a lot of older relay and protective systems in the field still. We're constantly evolving and changing that to newer technology. So in those areas where we have not migrated to a new technology, we will be most likely adding this device for battery monitoring.
Also, you mentioned that this is a cost-effective solution to the tune of about $30,000. So can you give me a number to compare that with, say, if something did fail, what could the possible financial ramifications be?
Well, the possible financial ramifications are when we lose control and visibility to a substation, first and foremost, we have to have someone staffed there 24/7 to maintain visibility. If our dispatch center loses visibility at a substation, it's an automatic babysit it until things are restored. Depends on the system that fails. If we have a DC battery bank fails, it could be, thousands of dollars and even a few days, if not a week or two, to get a new system in place. So as it's pretty critical. We mentioned reference to the NERC, which is something that is constantly evolving, and what we're trying to accomplish. We're rolling out new regs all the time on us. We're trying to keep ahead of the curve a little bit and try to maintain visibility of these systems, whereas in the past, we did not, and most utilities did not monitor this. So,
Thank you. Any other questions? All right, let's give them a hand.